So here is another way how to measure the nuclear radius, this time using electron or neutron diffraction, which is actually a property of waves. Remember, de Broglie hypothesized that particles can behave as waves with a wavelength h upon p. So if the diameter of the nucleus is the order of magnitude same size as the wavelength of the electron, what happens is the electron wave can diffract around the object and over here on a screen we can observe a diffraction pattern. So we would get a bright spot in the middle, and then we get a minimum and a maxima. Sometimes you'll even see this as rings if it's a circular, or you will actually see rings since the object you are diffracting around is a circle. And by measuring the angle to the first diffraction minimum, we can use the fact that sine theta is approximately equal to lambda over b, where b is the size of the obstacle, in this case the diameter of the nucleus, in order to find b. So let's have an example. We have a beam of neutrons. This time, so just scratch that. Let's say we have neutrons now here, and we give them an energy (85 MeV). We fire them at a foil made of lead and they're diffracted, and we observe a first diffraction minimum at 13 degrees from the central position. Estimate the radius of the lead nucleus. So the first thing we need to do is work out the momentum, and the momentum we get using the formula 2 times the kinetic energy, or the square root of 2 times the kinetic energy times the mass. That's from kinetic energy equals momentum squared over 2m. Plugging in some values here, square root 2 times 85 mass of lead, and sorry, no, this is the energy with which we accelerate them, 85 mega, and then to get in joules we have to times by 1.6 times 10 to the negative 19 times the mass of a neutron, 1.67 times 10 to the negative 27. You get out this in the order of magnitude of 10 to the negative 19 Newton seconds. 2.3 times 10 to the negative 19 Newton seconds. Use this, plug this P into the formula for the wavelength, 6.6 times 10 to the negative 34 divided by 2.13 times 10 to the negative 19. You get a wavelength approximately equal to 3.1 times 10 to the negative 10. So we know the diameter of the nucleus is going to be roughly of this order of magnitude, since we see a diffraction pattern, and you get diffraction when the order of the obstacle is of the same size as the wavelength. So therefore, if we plug this, or rather if we plug this value of wavelength into here and solve for b, we get b equals 3.1 times 10 to the negative 10 divided by sine 13 degrees, which is approximately 14 times 10 to the negative 15 meters, which actually is corresponding to a radius of half that amount, 7 times 10 to the negative 15, which is meters, which is a fairly good agreement.